This is this is Engineering Statistics and Linear Algebra 18 EC 44. We are in the module 1 and we are in the module 1 which corresponds to the single random variable, and today we'll try to do the conditioned random variable. Condition or conditional random variable. Before going to this, we'll try to solve the problems, one or two problems there, and then we'll go for the conditioned random variables. So in the last class also, we took up this problem. The random variable is uniformly distributed between x equal to -2 and x equal to 3. Y is related to x. Using the plot which is shown over here, find the CDF and PDF for the random variable y. So now what is given is this figure, but for this we should be able to convert it into an expression, and this is not given to us. So therefore from this figure we can write y is equal to, you can see that for all positive values of x, for all positive values of x, on the positive side the value of y is 2, on the negative side that means for all x less than 0 the value is -1. So you can write over here y is equal to 2 for x greater than 0 and y is equal to -1 for x less than 0. Further to this, if you see over here, what is written is a, what you call x is a random variable which is uniformly distributed between x equal to -2 and x equal to 3, and that will give us the, what you call, PDF, the probability density function like this. Between -2 and 3, it is uniformly distributed, it is constant. Now from -2 to 3, the range of values will be totally 3 minus of -2, that will be 5. Now because this is 5, the maximum value over here or uniform value over here is 1 by 5, that is equal to 0.2, because the area of this should be equal to 1. The area of this should be equal to 1. Now with overall, this is the PDF. Once we know the PDF, we can write the what you call CDF, and the CDF is, again, CDF is here for the fxx, that is the x random variable. Now because now this is a constant, the value of the CDF will be slowly increasing from -2. At -2 it will be 0, slowly it will increase. At 3 it will be equal to 1. Okay, at 3 it will be equal to 1. Okay, that is the way in which, because if you integrate this, you will get this value. So integrating this, at this point it will be 0, then slowly it will increase and it will end up at 1 over here, right? It will end up at 1 over here. Now writing the equation for this straight line will give us the value of f of x, and below -2 it will be 0, above what you call 3 it will be 1. Below -2 the CDF is 0, above 3 it will be 1. Between this it will be the equation of the straight line. Further to this, okay, further to this, we can try to write the value over here, right? Now we can say for x less than 0, if you see this here, for x less than 0, the area is, the area here, this part of the area is 0.4. This part of the area is 0.4, and for the value which is greater than 0, the area of this will be 0.6. You can find the area something like this. This is a triangle. The, what you call, base is 2. 2 into 0.4 by 2, half into base into height, will give us the area, which will be 0.4. The area here is nothing but the difference between 1 minus 0.4, and that will give us the value of 0.6. Or otherwise, what you can do is, half of base is 3, so that will give us 3 by 2. Into h1 plus h2. h1 is 0.4 and h2 is 1. So 1.4 into 3 by 2. Okay, 1.4 into 3 by 2. That will give us the value which will be equal to the 0.6. Okay, that will be the value which will give us as 0.6, right? Okay. So that will be the area over here. So this is 0.4 and this will be 0.6, right? This will be 0.4 and this will be 0.6, right? So the area here is for x greater than 0, it will be 0.4. For x less than 0, it will be, for x greater than 0, it will be 0.6. For x less than 0, the area is 0.4. So therefore, now we need to compare this with this. You can see for all values of x positive, it is equal to 2. For all values of x negative, it is equal to -1. So here, for all values of x 0, the value of y is less than 0. For all values of x less than 0, the value of y is -1. For all values of x greater than 0, the value of y is 2. So therefore, this will give us, in place of this, we can try to write y, the p of y minus 1 will give us the 0.4, because that will correspond to x less than 0. And p of y equal to 2 is equal to 0.6, because that will correspond to x greater than 0. When x is less than 0, then y is -1. When x is greater than 0, y is the value 2. And therefore, the probability also will be like this. So therefore, the what you call the CDF for the y variable will be nothing but P of y equal to -1, U of y plus 1 plus P of y equal to 2 into U of y minus 2. So this will be 0.4 U of this and 0.6 U of this. So we will now need to calculate the what you call PDF for this. This is the CDF for y, and this is the PDF for y. PDF for y will be equal to the dy of fyy equal to 0.4 del of y plus 1 plus 0.6 del of y minus 2. If you just differentiate the what you call unit, function, right? This is step function, unit step function. Then you will get the unit impulse function correspondingly delayed. Similarly, this is also unit function which is correspondingly delayed. We'll get the unit step, this is the step function, and this is the impulse function. This is the unit function, this is the impulse function. So if you differentiate the step function, we'll get the impulse function. Thus, we can solve the 81 problem. Now let us go to the problem number 73, which we did not solve in the last class. So let us see what it is. If you have any doubts, you can ask in the earlier problem. If you the random variable x is uniformly distributed between plus or minus 2. The function gx is given as y is equal to gx equal to x squared for x greater than or equal to 0 and minus x squared for x less than 0. What are the CDF and the PDF for y? So we need to consider this function for x. Okay, so the value between plus or minus 2, it is uniformly distributed. X is uniformly distributed. So between -2 to +2, it is uniformly distributed. So that's why we can write the figure something like this. From -2 to 2, it is uniformly distributed, and the x value, the width over here is equal to 4. From 2 to -2, 2 minus of -2 will give us the value 4. So therefore, its height should be 1/4, because the area under the PDF should be equal to 1, not under CDF. Please remember that area under the PDF is equal to 1. And because this is 1/4, the height should be, because this is 4, the height should be 1/4. Okay. So having got this, you can write it like this also for this. First, we should write this figure, and then you can write this. So the value between -2 to 2 for the PDF value is 1/4 and 0 otherwise. Now, if you integrate this, we will get the value which is something like this, with the figure which is something like this. At -2, it will be 0. At 2, it will be 1. And naturally, it is going to intersect at exactly the y-axis at 0.5, because it is almost symmetrical. You can see that it is symmetrical. So this will be 0.5. Okay, this will be 0.5 on both the sides. You have the equivalent value 2 and -2. 0 and 1 means it should be exactly at 0.5. That doesn't matter. However, we can try to write at for values the CDF over here. For values below -2, it will be what you call 0. This should be -2. For x less than -2, it is 0. For values greater than 2, it will be 1, this value at the top. And between -2 and +2, so this should be, sorry, -2 and +2, change this to -2 and +2. This should be -2, and this will be -2 to +2. Between -2 to +2, this value, this should be, we should write the equation of the straight line. So if you write the equation of the straight line, then you can write it as mx plus c, where m is the slope of the line. The slope of the line is naturally 1 by 4. Okay, the slope of the line is 1 by 4 because this value is 4 and this value is 1. 1 by 4 will give you the slope of the line. So that's why 1 by 4 x, or x by 4. And the intercept, the y-intercept over here is 0.5. Therefore, you can write it as 0.5. Otherwise, also what you can write is this is -2 comma 0. This is 2 comma 1. So you have 2 points. You can try to write the equation of the straight line, which will again turn out to be the same thing over here. Okay? There are different methods of finding the what you call equation of the straight line. One is mx plus c. Another is m into x minus x1 plus m into so to say y is equal to y minus y1 is equal to m into x minus x1. So using that, you can try to find out the value of the what you call fxx. Okay, you can find the value of fxx. Okay, so where fxx will be equal to the value of y over here. Now we are given the value of y as x squared for x greater than or equal to 0 and minus x squared for x less than 0. So having written this, naturally, the figure corresponding to this will be something like this. X is, if what you call x is positive, that is on this side, the value of y is x squared. So which will go on increasing like this. When x is less than 0, then we will have less than 0 means this side. The value of y is, negative x squared, minus of x squared. So the square of the minus quantity will also be plus, but in addition, we have here a minus. Say, for example, x is -2. If x is -2, x squared will be equal to, 4, and minus of x squared will be equal to -4. That is why it will be like this. So having written this, then how we can represent the value of x, other way around. Here we have written y in terms of x. How we can write x in terms of y is what we have done over here. So if this is the figure, this is y is equal to x squared, then naturally x will be equal to root of y. And that is why we have this value for all values of y greater than 0. For all values of y which are positive, we have root of y. For all values of y which are negative, we need to go for this. And that will be, if you take this minus, you have to take on this side, and x squared will be equal to minus y. X will be equal to, plus or minus root of what you call minus y. But we should take the negative value because, here we have the value of x which is, negative, as well as y is negative. So therefore, we are taking here plus root y, here minus of root of minus y for all the values of y less than 0. Okay, for all the values of y less than 0. So having written this value, we need to find out the fyy. Fyy is equal to p of y less than y. Now y less than y will just correspond to, two different things in x, and that will give us the value p of x less than y and p of x less than, minus of what you call, this is x less than or equal to root of y. this is x less than or equal to minus of root of minus y. Okay, these two different values, because we have here the quantities which are, y and minus y. So corresponding to this, we will get here fx of root of y, and this is fx of minus y, and this will give us the value which is, the equation for, this will be 0.25 root of y plus 2 for values between 0 to y to 4, and for this it is 0.25 minus of root of minus y plus 2, and this we can get easily from the value which we have written over here. Okay, this is the value which we have written over here, right? So wherever x is there, you write the value of root of y. In the first case, wherever x is there, you write the value of minus root of y in the second case. So either you write like this, or you can write, 0.25 root of y plus 0.5. Here you can write 0.5 into minus root y plus 0.5. Okay, in place of 0.5, we have written like this, but it is just same. Okay, same 0.5 here as well as 0.25 into 2 is 0.5. Okay, so don't get confused. This 0.25 into 2 is also 0.5 itself. So having got this for the CDF over here, the PDF can be found by just differentiating the CDF. So if you differentiate this with respect to this, you will get 0.25. The what you call differential of this quantity is root of y is 1 by 2 root y. The differential of 2 is 0, and therefore we will get the value as 0.251 by 2 root y. This is nothing but 1 by 8 root y between 0 to 4. Similarly, we will get over here the value 1 by 2 of root of minus y with a negative, internal derivative of minus y, that will be minus 1. So minus will cancel. Again, we will get 1 by 8 root of minus y for values of y negative. For values of y negative. Please remember that because y values are negative here, if you try to substitute the value of y which is negative here, it is going to become positive. Because the y of value are positive here, if you write a positive value, you will get root of positive value. So this is also root of positive value. This is also root of positive value. That is because here y is positive. Here y is negative. Negative of negative will become positive. Okay, that is how we can find the value of the PDF. That is how we can find the value of the PDF. Okay, so now having finished this, okay, other numericals you can try to solve the exercises of it, or rather the solutions of it. I have already put on the Google Classroom. Now we will go for the what you call conditioned random variable. Okay, conditioned random variable. So let us go for the conditioned random variable topic, which is similar to the conditioned probability or conditional probability. Okay, corresponding to the conditional probability, we have conditioned random variable. Okay, so conditioned random variable means here we will assume that the random variable x is defined and we know it. Okay, defined means we know the value, that is PDF for fxx is known. Now we will put certain condition for this x. So there is some event b which is conditioned for the observations of x. So in that case, then we need to find out the f of x given b or conditioned b of x. Probability, this is the probability density function for x given b of x. We can find out in the same way as we might have found the normal probability. Okay, so in that sense, if we take over here, so assume that we are given a random variable x with its PDF and CDF. Further, assume that some conditioning event b is also given, and this conditioning event is b equal to having values of x between x1 x2. Okay, b is having values of x between x1 x2. That's the condition. So the what you call CDF the CDF over here, conditioned CDF, so to say, is given by over here as capital F of x given b, or x conditioned with b of x will be equal to p of x less than x intersection of b. This will give us intersection of b divided by p of b divided by p of b. Similar to this is just, if you remember, this is similar to our conditioned probability where pb is greater than 0. Okay, and what is this? What is this numerator over here? P of some quantity, and this quantity is nothing but the value which is x less than x. Okay, intersection, the value of b is in between x1 to x2, x1 to x2. So here we have x less than x, here we have x between x1 to x2. So in case we have values of x between minus infinity to x1, there won't be any overlapping portion between these two. If x is between minus infinity to x1, this and this do not overlap. Because this and this do not overlap, we will have their intersection to be corresponding to a null. Okay, when we take this for the what you call x, then this portion and this portion no overlap, and that will give us a null. If the value of x is between x1 and x2, both are between x1 and x2, naturally their intersection also will be between x1 and x2. Both will be between x1 and x2. So that hence we will get the value over here like this. Now, if the value of the x is above x2, if the value of the value is above x2, then whatever is there here is covered within this, and therefore it will be equal to the b itself. Whatever is there here is covered within this, so therefore intersection of that will be this quantity itself, which will be b. This quantity itself, which will be b. Okay, so this will be x1 to x, this will be b itself, this will be the value which is phi. So writing it in the figure for the PDF, if PDF without condition is this, and that will give us fxx, and if PB is within the range x1 and x2, then the conditioned PDF will have a figure which is like this. Will have a figure which is like this. Remember that the area of this should be equal to 1. The area of this should be equal to 1, because this is probability density function. The area under the probability density function should always be equal to 1. Okay, area under the probability density function totally here will be equal to 1. So that just means if we take within the range, height is going to increase. Height is going to increase because totally the area should be equal to 1. So applying these three cases to our equation, which is 2.114, that is this over here, then we will get here the conditioned CDF to be 0 between minus infinity to x1, and between x1 and x2 it will be fxx minus fxx1 by pb, and 1 for all values greater than x2. Okay, and the conditioned PDF will be just the differential of this. If you differentiate 0, you'll get 0. If you differentiate this, you'll get again 0, because this is also a constant and this is also a constant. Only the differential of this will give us the value which is something like this, because if you differentiate this, we'll get the PDF corresponding to this. This is just a constant. This is also a constant. Differential of a constant will give a value 0 here, and therefore we'll get the differential of this divided by p of b, and the differential of this is nothing but fx, the PDF corresponding to f, x PDF corresponding to x divided by p of b within the range x1 to x2. So if you differentiate the CDF, we will get the PDF. We will get the PDF. Okay. So continuing from there, we can write the conditioned probability, whether it is conditioned probability or the whatever we have written here is the differentiation. If you take the inverse of this, then this conditioned CDF will be the integration of the conditioned PDF. Okay, so that's what is written over here. The conditioned CDF will be equal to the integration of the conditioned PDF, which will be the inverse of whatever we have written over here, which is nothing but the conditioned PDF will be the differentiation of the conditioned CDF. Okay, so this will be the formula for inverse. Going on a what you call for the um, first moment, second moment, and so on, which are basically expectations. Expectation of a function g of x conditioned, so to say, expectation will be equal to the g of x, f of x. This is again f of x conditioned with b of x. So that means here this will be the conditioned, PDF. This is the function gx, and we are trying to find the, so to say, the expectation of a function gx conditioned by b. Okay, so this itself is nothing but the what you call, in particular, if we take in place of g of x, then we'll get the what you call mu, and that will be the mean correspondingly, and mean, which is again conditioned, will be equal to x fx b x dx. So this is the conditioned PDF. Similarly, the second movement, which is again conditioned for x, will be having this formula, and similarly the variance, which is conditioned, will have this formula. Okay, so let us take the numerical, which is here with respect to the conditioned PDF. Okay, with respect to the conditioned PDF, I'll stop the what you call